Interesting story here out of the United Arab Emirates. They're planning to drag an iceberg from Antarctica to provide drinking water for millions. The UAE is at a serious risk of droughts over the next 25 years due to its climate. One iceberg could provide enough for 1 million people over 5 years. Wow. An eco firm plans to tow them around 5,500 miles or 8,800 kilometers to harvest water. Welcome back. We're back with Dr. Ben Tippett from the University of British Columbia talking about time travel. And what about black holes and wormholes? Could they hold perhaps the key or the answer to time travel, either to the future or the past?
Oh, well, black holes are really fun. So, as you know, the thing about black holes is they have a boundary, the event horizon that you can't. It's a one-way journey. You can only pass one direction through the event horizon, and if you go through, you can't come out, right?
Correct.
But if you have a spinning black hole, something really weird happens, which is earlier we talked about how there are some things that we theorize kind of out in space, mathematically possible, where you can go in there and travel into your own past. If you're near the center of a spinning black hole, you can actually travel into your own past. The only past that is accessible inside a spinning black hole is since you entered the black hole. But
okay. So it would be your very recent past.
Yeah, right. And also, it's really crappy. Can I say that?
It's the crappiest form of time travel. Yes, I agree.
Yeah.
It's the crappiest form it's a poor man's time travel.
You don't want to do that. Wormholes, on the other hand, wormholes have been theorized as a way. Well, how should I put it? Kip Thorne's group. Kip Thorne is a theoretical physicist. He was involved in. You remember that movie? It was called Interstellar. It came out a few years ago. It had these gorgeous pictures of computer-generated black holes. Right. So Kip Thorne was like the technical guy who helped them with that. He's a very, very important physicist in my field. And one of the things he pondered about in the late 90s was time travel and how time travel affects things like causality. And the mechanism he came up with for time travel involved wormholes. So fantastically, yes, you can use wormholes to travel in time. There's a big issue with that, several, but one of the big issues is if you go into a wormhole, if one existed, if you went into it, it would collapse and instantly become a black hole. And then, you remember how I said the inside of the black hole is a really bad place to be?
Correct.
Yeah, you'd be stuck there. Terrible. There's a way to hold, so wormholes immediately collapse as soon as anything passes through them, mathematically. So the way to hold them open, you can hold open the door using exotic matter. Last half hour we talked about exotic matter. It creates a type of space-time curvature that we've never seen before, a type of curvature that's gravitationally repulsive. So if you had a wormhole, you could hold it open, you could plaster the walls of the tunnel through space-time using this exotic matter, and sure, travel through time using it. So,
all right, yes, fill your boots. All right, Gordon is in Lakeland, Florida. Good morning, Gordon.
Thank you for taking my call, Richard. Dr. Tippett, first off, I wanted you to address a little area of confusion. We know that velocity will slow down time because if a light beam is bouncing back and forth and you're going forward, it cannot go faster than the speed of light. So the hypotenuse is going to be the speed of light. And so the forward motion will slow down a little bit. But I want you to explain how gravitation, which is another form of acceleration, will slow down time. And secondly, if you were to use a time travel machine and you were to go forward or backward, and the Earth is on its axis, when it moves around, it'd be like the Enterprise beaming you into space because you would be in a different place. I want you to address how that might be overcome, or if not. But the issue of the acceleration, a.k.a. gravity, because gravity is a form of acceleration, slowing down time, is something that does slow down time, but I don't quite know how. And if you can remember those questions, I'll listen in, and if not, I'll stay on air instead of, the opposite of going off air. I'll travel backwards in time. How's that?
I appreciate that, Gordon. Did you actually say the hypotenuse is the speed of light?
Well, I understood. Yeah, he did. He's talking about the light clock. It's a thought experiment that Einstein came up with to explain why time slows down the faster you're traveling. Fantastic question, Gordon. So Gordon was talking about the speed of light and how nothing can travel faster than the speed of light. It's definitely true. this is special relativity. He came up with this in the early 1900s, before 1910 sometime. I forget the exact date. So that's the theory of special relativity. It depends on space-time existing. Fantastic theory. The theory that we're introducing today is called general relativity. I think you have some sense of this. General relativity is about space-time being curved and causing gravity, among other things. And those other things, one of them is the possibility of time travel. So, in general relativity, nothing near you can travel faster than the speed of light. That's still true, but you can compare one point to another point, and the deal is that if you're far away from something, the gravitation, so the space-time curvature between the two of you can cause the direction of time to be different way over there than it is close to you. In fact, one of the things you might be familiar with is black holes. We've been talking about black holes. The further down you get inside of a gravitational well, the slower time passes for you. That's definitely true. The thing about the event horizon, the reason why you can't pass through it is because if you pass through the event horizon, at or near the event horizon, time, the direction, the arrow of time kind of points sideways in a way that's difficult to explain without a nice piece of paper to write all of it out on. But it's curvature that causes this effect. You can have different directions of time inside your space-time caused by curvature, and the long and the short of it is that through curvature, you can make it so that one object looks like it's traveling faster than the speed of light compared to another object, even though both of them are satisfying this special relativity condition that everything nearby each object isn't travel. Oh, boy. Everybody's lost on that one.
No, nicely done. All right. Joe is in British Columbia. Joe, good morning.
Hello.
Hi there, Joe.
Hello,
You're on.
Joe.
Hello to you and hello to your guest. Well, I have a question from your guest about time travel.
Mm-hmm.
All right, let's have it, Joe.
Yeah, if that time travel that your guest is talking about, is it a physical travel or a spiritual travel? Because I know a spirit goes back to the fourth dimension, which is the ethereal dimension, and then it gets information and then can get back, or it goes to the ethereal dimension, get the information about the future and past. But I'm not sure about physical body. Is he talking about the physical body traveling, going to the back, or a spiritual body?
All right.
That's a wonderful question. Okay, so this is about the physical body traveling back and forth through time. I've heard in fact, this very show, people talking a lot about spiritual time travel, and there's an important distinction between those descriptions and mine, which it's a mathematics. Because of Einstein, the great genius that he was, we have a mathematical framework that lets us set up descriptions of this physical time travel that we can then analyze and say, is this physically possible? What's the probability of this ever happening? Whereas spiritual time travel, we have no method of quantifying or testing it, or even describing it in some kind of concrete way. And so very little can be said on my part about spiritual time travel because we have no method to study it or describe it. So this is physical time travel we're talking about.
All right, Joe, thank you for checking in from British Columbia. And let's see, Max is in Junction, Texas. Max, good morning.
Hello. Can you hear me?
Loud and clear.
Okay, great show. Dr. Tippett, what about, have you heard about Marshall Barnes' work?
I haven't.
Okay, he's one to look into. And when you were talking about spinning black holes, I guess you were talking about Roy Kerr's work.
That's the very one.
Okay.
Marshall is working on another. Marshall is working on another time machine.
Oh, I see.
Negentropy.
Sorry, can you repeat your question?
Have you heard about negentropy, negative entropy?
Well, in this context, I haven't. But entropy is definitely something that gets studied in the context
how
of
about
black
the
holes.
Einstein-Rosen bridge?
Oh, sure. That's a description of a wormhole. Yep.
Yeah. I read Kip Thorne's book, Wormhole. What about, let's see, I don't know what else to ask you. Anti-gravity, would that create a time machine?
Well, essentially, that's what we're saying. You would need some kind of material that gives anti-gravity, that causes the kind of curvature for anti-gravity in order to build a time machine. And we've never detected any of this material in our labs before.
All right, Max. By the way, what is the latest? Can you give us an update on Marshall Barnes? He's working on another time travel device or theoretical device. What's the latest from Marshall? I haven't heard from him in a while, or about him in a while.
Yeah, the Tesla Cube he's trying to do.
All right, might be worth getting Marshall back on the program.
And the Zeitnauts, Zeitnaut. But have y'all heard of Kurt Gödel's theorem?
Oh, sure.
Yeah. That's probably the key to it, that or the wow signal, maybe. Anyway, thank you for your show. I really enjoyed it. And
all right,
have
Max.
you heard of Andy Basiago?
Yes.
No, I haven't.
Well, he's Andy claims he was part of a military time travel project called Project Pegasus back in the late 60s and 70s, and that he was transported back and forward in time. At one point, he maintains he traveled back and witnessed the Gettysburg Address. So there you go. West of the Rockies, Howard is in Vancouver, Washington.
Hello, Richard and Dr. Tippett.
Hi there.
Hello.
I've been accused of being a throwback, so I guess I have a vested interest in this subject. I've heard a lot about the Mandela effect, where many people remember recent history differently than what it really was. I wondered if you had any comment on that.
Right. That's I've been hearing a lot about that. Are you familiar with the Mandela effect, Ben?
Oh, sure. Can I summarize it for the audience?
Yes, please.
Okay, so the Mandela effect is the feeling you get when you read history or news that summarizes history where you say, I don't remember it being that way. So a bunch of people remember Nelson Mandela being assassinated while he was in jail, and then he wasn't. He lived through his jail term and eventually became the president of South Africa. And so they said, "Oh, I thought he died in the 90s," but no, he didn't. And so the argument behind the Mandela effect is that maybe people are switching universes. The reason everybody is so up in not arms, is very excited about it, is because with the Berenstain Bears kids book, right?
Right.
The way the Berenstain in Berenstain Bears is spelled isn't Berenstein, S-T-E-I-N. It's Berenstain, and everybody read it and said, I don't remember it spelled that way. Oh, so I've been complaining to my wife several years before everybody blew up about the Mandela effect, about how confused I was at some recent point in history that I'd misremembered. And I said, well, maybe I switched universes and the universe is wrong. And she told me to stop talking that way because everybody would get mad at me. But here I am predicting something that everybody on the internet would be excited about several years in advance.
I'm going to use that. I'm right and the universe is wrong. The next time I'm in traffic
right.
court.
Yeah, every time I get a fact now wrong, I'd say, well, I've just switched universes. So I think the thing that everybody's really excited about with the Mandela effect kind of has a tie-in to Kip Thorne's wormhole black hole model. So have you heard about this? I'm not sure. It has to do with the many worlds theory of quantum mechanics.
Right.
And the argument is that some people don't like, we spoke last hour about Novikov's self-consistency condition that says that you can't change the past. And lots of people don't like that about our physical models of time travel. And so they said, wouldn't it be great if you could change the past? And everybody kind of shrugs. And so one interpretation of Kip Thorne's wormhole method is, what if the wormhole didn't transport you back into your own time? What if the other mouth of the wormhole was in some other parallel universe, exactly the same as our own, but in that universe you could muck around with the past all you want because the future wouldn't be set in stone. What those people would say is, hey, this person from the future didn't come back and putz with it. What they would say is, somebody came out of this wormhole from who knows what universe and then started affecting the causal order of things. And so the argument is here, maybe there are lots and lots and lots and lots and lots of different parallel universes, and maybe in one of them Bernstein Bears is spelled one way, and in another universe Berenstain Bears is spelled another way, and we've hopped between the universes somehow. I'm not sure if I buy it, but it's pretty...
I think can we squeeze one more on? I think so. Let's go. Barry is in South Carolina. Barry, good morning.
Hello there, Richard. It's Barry Poole in Rock Hill, South Carolina, and got a degree in biology and chemistry and some background in astronomy and physics. And I tell you what, I just want to ask your guest, the heck with the past. If I had a chance, I want to go 1 million years into the future. And what do you think it's like?
1 million years into the future. Well, if we're still here, that's a good question. So you'd rather travel to the future than the past?
I want to go 1 million years into the future.
Why 1 million?
Yeah, 1 million or 500,000, you know. I'm so curious about what's going to happen to mankind and evolution. I believe in evolution too, but I believe that there's a long-term future for the human race, and I'm just curious to know what it's going to be like, and just wondering what your guests thought.
All right, Ben, any thoughts on that? Traveling 1 million years into the future. My only hope is that the Leafs, by that point, will have won a Stanley Cup.
I'm not sure if that'll ever happen.
Oh, dear.
Well, let's see. Boy, you know, I'm not sure if humankind's going to be around in 1 million years. I think lots of, humankind hasn't been around for 1 million years, certainly. And the way we're going, we're certainly about to affect things in very cataclysmic ways. Global warming is going to mess up a bunch of things. I think in the short-term future, in the order of several thousands of years, we're going to see this global extinction event that we're slowly causing really taking root. And then I don't know if human civilization will last through that, to be honest. But whatever happens will grow on the bones of whatever's left, and so we'll probably see a lot of weird things evolving that can stand really hot temperatures and the 150-degree Fahrenheit summers around the equator and all the other weird remnants of the climate change that we're about to leave behind. Boy, there's going to be some weird life 1 million years in the future. I'm not sure if that's long enough for intelligent life to reemerge, though. Ooh, scary. It'll be a lonely future, I think. Yeah.
Barry, thank you for giving us some food for thought there. We'll head on into a break here shortly, and then back on the other side, more calls. People just are filling the lines. Time travel, always a popular subject, and Dr. Ben Tippett doing terrific work here answering your questions. Stephen Hawking had a great question. If time travel is possible, where are the tourists from the future? Dr. Ben Tippett, theoretical physicist from the University of British Columbia. We're talking time travel. What about time travel to the future? Is that, I mean, I know that that time dilation, we've proved that with, the atomic clocks, one on the ground, one on the plane, and so forth. But I mean actual time travel to, the distant future, for example. Is that any more feasible than time travel to the past? Or do we still run up against that exotic matter issue?
Well, the nice thing about that is you don't run on... Well, you can use exotic matter to do all sorts of really fun things, but you don't necessarily need to have exotic matter to travel into the distant future. You can just get a rocket ship, a really, really, really big rocket ship, and just accelerate, going on a grand tour of the galaxy, come back in 10 years' time, and it will be the distant future if you went fast enough for long enough. The big thing about that is even that isn't all that plausible. See, the universe is full of radiation and random atoms, molecules just kind of floating out in space. And if you're traveling nearly the speed of light in a spaceship, those atoms and rocks and bits of dust and even photons are going to hit your spaceship at nearly the speed of light, and they'll cook you inside it. So I think we're kind of stuck in this current era, whether we like it or not, to be perfectly honest. But it's definitely something that's way more plausible than going backwards in time, unfortunately.
What about not sending a human into the future, but just like a particle of data or information?
Well, even then, yeah, certainly. I mean, people bury time capsules. That's a type of a way to send data into the future at 1 second per second. Yeah, certainly. I mean, we have sent out, the Voyager probes, and they are leaving the solar system as we speak, and they're traveling much faster than we are. So time is moving slower than ours in some perspectives. So if they ever make the journey back to Earth somehow after a few tours of the galaxy, they'll have transported that great golden disk with all that fantastic music on it to our distant descendants.
All right. Jane is in Biloxi, Mississippi. Jane, good morning. Welcome to Coast.
Oh, hi, y'all. Can you hear me?
Loud and clear, Jane.
Okay. First of all, I really am so honored to be listening to you, Mr. Tippett, then Dr. Professor. I'm not really sure which one you'd like to be called. I usually call my teachers Professor. So, and you too, Richard. Thank you for having me on.
Thank you.
Now, first of all, I didn't catch the very first of the show, and I was hoping that I could get information on your contact information, Dr. Tippett, if you are available to maybe possibly the general public to, ask questions, challenge, or not challenge you, but challenge the general public, that is lay people that don't really know much about this stuff.
Well, let's see. You can follow me on Twitter if you'd like. It's at DNPRIME. I have several email addresses, and if you send them to my academic address with all my students, you'll tend to get kind of filtered out because there's always people asking me really, really important questions about whatever course we're taking. So I have contact information on my public webpage. It's at www.titaniumphysics.com. www.titaniumphysics.com. It's the home of my physics podcast where my friends and I explain complicated physics, as complicated as this is, to general lay people, and it's lots of fun. So on that website, you can find my email address and pop me a line.
Titaniumphysics.com.
Titaniumphysics.com. Yeah, it's the Titanium Physicists podcast, if you like F's and PH's and S's on your radio. Yeah.
Okay,
all right, Jane.
I really thank you, Dr. Tippett, and I've had a little bit of education, but still working on my bachelor's of psychology, so I don't really know much about this stuff, but I have a big interest in learning. Several years ago, well, there's two different things I'd like to ask you. First of all, could the past be like when you go to those picture booths, just a little cheap picture booth and get a picture with your friend or whatever, and it has a picture, then it has a separation, and then it has another picture and a separation, and each of those separate pictures are permanently fixed in the universe. And it say that continued, the pictures with the separation. And it was kind of like still frames. And you went back into one of those particular frames. Would it be the same? Let's say you went back there, and then you came in the present again. You thought, okay, I'll go back and see if it's exactly the same. Will it be the same? And how much daddling can you do there? Or are you kind of like just an onlooker? And that's kind of the first question I wanted to ask you.
All right, Jane.
Let's see. Suppose as a teenager you went into that photo booth and you had your photos taken, but then suppose that your mother ran up and snatched the photos before they developed and put them in her purse and ushered you off. So you never got to see the photos. And then you took a time machine, one of these time machines that we've been talking about, into the past to that very day, and you decided to, everybody's sitting in front of the camera, and you decided to stick your head in behind your teenage self and get your photo taken with it. The deal is, you can, in the past, you can interact with it as much as you do with anything in the current day. And if you went to your mother's purse, you would see that the original photos that had been taken had your adult face sticking in behind. That's what we mean when we say we can't change the past. Any interaction you do in the past is fine, but it was always that way. You were always in the past mucking with your future self, mucking around with your past self. So it's not like you're stuck in the past watching everything like a television. You are able to do some things, but I mean, I guess that's all there is to say about it.
It makes sense.
Insofar as you can't build one of these time machines, but if you could, you would be able to.
All right, Jane, did you have another question?
Yes, and first of all, there's got to be a starting point, though, I suppose. Well, of course. I'm sorry, I just answered my own question. The next one is, and I know this seems kind of off the wall, and I hope to goodness this doesn't sound too crazy, but I've started to find things just out of the blue, things that look like things that might be my things, like hair bands and certain lighters that I've had that were the same color as my lighter and the same this and that. And I don't know, I've kind of got an oddball thinking that possibly maybe it could be my future self dropping these things possibly, and maybe kind of as an encouragement to, okay, keep on going, you'll be all right kind of thing. I don't know.
Well, that's a very sweet story. I'm not sure if it's true, but I definitely think you deserve encouragement. Keep on going. Everything's going to be fine. Work hard. Yeah, I mean, it's hard to say, right? Until you are 80 years old and you say to yourself, I have never traveled in time. That was definitely not my lighter. Or alternatively, you're, a couple years from now, somebody does get their hand on exotic matter and you do travel into your own past and you do leave all these things for you. There's no way to know if it is or not, but everybody needs encouragement, right?
Absolutely. Jane, thank you. Very interesting questions, both. Carlos is in Gulfport, Mississippi. Good morning, Carlos.
Thank you for taking the call. I've got two questions. I'll try and make them brief and take my answer on the air. My first question is regarding prior existing matter. For example, let's say you built your time machine today in 2017, and you wanted to go back to 2000, but in the same spot where the time machine is now, as you're traveling back, say, in 2010, there was a pinball machine. Now, what happens when the matter of the time machine is traveling back to 2000, and would it interact with the prior existing matter of the pinball machine? My second question would be about how long would it take? You mentioned the person in the machine, time would still go forward for them, but would it take 17 years to get back to 2000, or would it go faster or slower? I'll take my answer from here. Thank you.
Great questions, Carlos. So what about matter that existed before? What happens?
Yeah, so okay, so we painted the picture that you get into your TARDIS booth, and then you turn it on, and it goes back in time. Fine, really exciting, perfect. We also mentioned that if you wanted to go back 100 years in time, that means that your TARDIS time booth is going to be sitting somewhere for 100 years as it moves backwards in time, right? So people would look in through the window of it and see you looking at your watch, waiting for your flight to arrive, everything going backwards inside the booth. Everybody would say, hey, look, that person inside the booth is making breakfast repeatedly in reverse. How exciting. So the long and story short is, as you're traveling back in time, you're inside of an object that exists in regular space, and so if something got in its way, it would hit it the way a car hits a pinball machine, say. Nothing so dramatic as you might expect. Let's see, what was the second question? The second question was
how about speed? Oh yeah, how long does it take? Yeah.
So unfortunately, it takes, for my mathematical model, it takes more time to go into the past than it does for the past interval to happen. How should I put it?
Wait, you mean if you wanted to travel back to the year 2000, it would take longer than 17 years?
Yes, it would. It would take maybe about, depending on where your destination, something like 3 times as long, give or take. It depends. But yeah, it will take longer in my mathematical model. So time does pass, well, it's hard to compare the rate that time is passing because you're essentially taking a very circuitous route through space-time. And so, yeah, lots of time passes just to go back.
So roughly 3 times, so that's 51 years to travel back in time to the year 2000, 17 years ago. Would you age 51 years?
Oh, yes. Yeah, certainly.
So by the time you got back, you'd be 102 or 102 years older.
Yeah, right.
Not very practical.
No, it's not very practical, but that's okay. It doesn't need to be practical. It's a time machine.
Exactly. What was I thinking? Michael's in Eugene, Oregon. Michael, good morning and welcome.
This question about time travel where it's like we're occupying a point in space, and you know, if you consider that the Earth is spinning at 1,000 miles an hour, and then it's traveling around the sun at, I'm looking at the figures right now, close to 70,000 miles an hour, and then the solar system's traveling through the galaxy at 420,000 miles an hour, and then the galaxy's going through the solar system at 2,200,000 miles an hour. It works out to 2,724,666 miles an hour that we're traveling at any given point, at any given time. So it's like, if you're going back in time, how are you going to calculate exactly where you were, let's say a year ago, in a point in space that, you know, times that many miles per hour over a year? I mean, that's an immense distance. You know, you'd have to be exact. Otherwise, you'd be right in the middle of space or something.
Sure. This is a lovely criticism because essentially what you're saying is that the mathematical model I built was very, very, very simple, and then in reality, things are actually calculation-wise much more complicated. And it's true because the mathematical model I built was a proof of concept that you can do this mathematical trick to build this type of TARDIS time machine. If you wanted to build one that sat on the surface of the Earth for 30 years, you could. It's a lot of math. But, you know, as soon as we discover exotic matter, I can get cracking on the more complicated math. Otherwise, I'll leave it for future time travelers to do.
All right. Perry is in Santa Barbara. Perry, good morning and welcome.
Good morning, and once again, thank you for your voice, sir. And I appreciate your ending when you thank us for our beautiful voices. And
thank you.
You're quite welcome. You're a real gentleman. And hello to Doctor. Hi.
Hello.
Yeah, I have a comment and then a question, because listening to all this wonderful knowledge, and I'll be very quick. You know, the Mandela effect. It's very interesting. I could have swore that 10 years ago I usually leave my talk radio shows on in my radio when I go to sleep. I could have swore that they said that Reverend Billy Graham died. It's not true. He's still with us.
Well, that does happen occasionally by mistake. A news organization will release an obituary. In fact, it happened recently, just before Prince Philip announced that he was stepping down from public appearances. Somebody released that either in a newspaper by mistake. That does happen. That's not to discount the Mandela effect. But
no, I don't want to discount it. Yeah, if you can discount it, well, it's a good explanation, Richard.
Oh, man, that's such a great explanation. You popped the Mandela effect, Richard.
There you go. What's next?
Quantum computers.
Bring it on.
That involves quantum physics.
Quantum computers. Trying to remember there's a physicist at Oxford who said quantum computers, once we have those, that will prove the multiverse theory.
Oh, interesting. So there's a mixture of things going on here. quantum mechanics is something that is both well understood. We, as physicists, we understand the mathematics of quantum mechanics very, very well, so much so that we've been able to build a quantum computer. So they exist, and they're capable of doing types of calculations that harness quantum superposition, very, very rare and complicated matter, doing computations with them. So it's absolutely fantastic that people have built these things. The thing about quantum mechanics is nobody's sure what story to tell to accompany the mathematics. So we know the mathematics works, but usually when physicists do a calculation, we like telling ourselves a story as it goes. We like saying, okay, this particle is going over here, and then this happens, and the particle goes over here, right? To end up with the thing that you're going to measure. So with quantum mechanics, we're not sure exactly which story to tell while we're doing the analysis. So one of the very old, very famous interpretations of quantum mechanics is the Copenhagen interpretation that involves wave functions that collapse.
We're going to have to leave that one to another time, unfortunately.
Okay.
Ben, my apologies.
Anyway.
I'd love to have you back on. I really enjoyed this 2 hours. Thank you so much.